So, welcome to the afternoon session. It's my great pleasure and honor to introduce our next keynote speaker, Professor Michel BRONIATOWSKI. Professor Michel BRONIATOWSKI is professor in statistics at Sorbonne University in the LSTA laboratory, which is a laboratory for theoretical and applied statistics. Michel is a pioneer in statistical divergence and duality methods for statistical inference. He is a long-time contributor to GSI, where he's researching the interplay of divergences with inference and model selection. And recently, Michel released with his colleague, Professor Stummer, a very nice archive report on minimization of statistical distance. So it's my great pleasure to have you today, Michel, with us, and I'll give you your talk now.
Okay, thank you very much. Well, thank you to the organizers for this very kind invitation, and to Sky. Where's how do you? So the talk is about some principles. This talk is about some principles in inferential inference and the limits of this approach. And this will be the first part of the talk. The second part will be situations and methods for which we're able to handle minimum distance problems in situations when variational methods may fail or may find a number of difficulties. The second part of the talk is joint work with my friend and colleague Wolfgang Stummer, and since I'm just recovering from some harsh difficulties, I will let my friend Wolfgang Stummer present the second part of the talk, which he kindly accepted. Thank you. OK. Alors, comment ça marche? Oh, the next one. Outline. So the first part of the talk, as I said, pertains to variational methods in statistics. So I will first focus on a number of criterions to be satisfied in order that a divergence would be well defined. Then we go to what we call a model in this respect, and then we go to variational representations and the issues, those are at hand with that, and the difficulties which we meet. And then we will go to a total change of paradigm and insert minimum distance or minimum divergence optimization, say, in the realm of a probabilistic kind of representation that will lead to methods of simulation type. Okay, so in order to define properly, at least for statisticians, a notion of discrepancy between two distributions, we have a number of conditions to be satisfied. The first set condition is quite obvious. We will have a measure that should be non-negative. This is a definition between probability measures. It will be extended a bit later. The second condition is called data processing inequality, and it means that the same change on the variables should result in a difference that should not be an increase between the corresponding image distributions. Third condition, wait a minute, this is it. Third condition seems natural. Also, the fact that when Q and P have disjoint support, the discrepancy should take maximal value is still at debate according to numerous situations and models. This is not an obvious condition. It should not be held for any divergence, in fact. Fourth condition is of statistical nature as such. We want that the possibility to discriminate between two distributions according with respect to a reference distribution and this can be stated in terms of statistical tests, should be reflected in an inequality between the distances. So if two distributions can be separated in a more convincing way, somewhat statistically, than the first one with respect to some other one, we would like this order, the statistical order resulting from those procedures, to be kept by the resulting divergence which we want to define. Now we have here the way we define divergences, at least a class of them, with respect to what is called sufficiency. If we have at hand a very limited model, restricted model, P0, P1, two distributions, and we consider an issue, so X from either P0 or P1, it can be seen that if instead of X, we consider P0 divided by P1 of X, then we have somehow exhausted all information from X with respect to these models, since we have the upper chain of equality. So you see that we do not learn anything longer from the source of the distribution as far as we have observed the likelihood ratio, we call it this way, P0 over P1. So any decision between and discrimination between P0 and P1 somehow could be made using only P0 over P1 of the observation X. This is indeed at the background somehow of what is called Neyman-Pearson lemma. So if we want to consider indexes of discrepancy between two distributions, it seems natural to consider functions of this ratio and obviously to take expectation of it, since we want to have a scalar number representing the distance between P0 and P1. This is the basis of what is called the Ali-Silve-Morimoto class of divergences. Okay. The fact that the function phi should be a convex function follows indeed from the need for the processing inequality. So this is a definition of a divergence between two probability measures we had on a finite alphabet, and this has been extended for necessity for various situations in statistics, and not only to the case when we want to define the distance, say, between a probability measure P and globally assigned measure, finite measure Q, from which we can give a number of examples. In the realm of statistical divergences, globally all, or mainly all tools which are commonly used in statistics fall in the field of this class of discrepancies, Jeffrey, Kullback, what we call the reverse Kullback, which is the likelihood divergence, Hellinger, and so forth. And we also have parametrized classes of such divergences we will work on mainly in the second part of the talk. Those are called power divergences. Okay, now we have to talk of models. The reason is the following. We will look at methods for making inference in a number of cases, and inference through the method which we will develop will not be accessible for all kinds of models. So I will first define a class of model on which we are able to make what is called variational inference. Here are a few examples. As you may read, some are somehow rather simple, not necessarily even parametric models, with the fact that we have situations for which the model itself bears a number of difficulties. For example, even simple mixture models bear difficulties when we enter in the set of the parameters the weight that may take value 0 or 1. So the point of the choice of the model, for example, with respect to the number of components, is a hard problem as such. But those are globally fields where we have a parametric model, so theta is globally embedded in a certain finite dimension. We have semi-parametric models. Some are simple in their nature. For example, the first one here, which is just the intersection of submodels which are linear. The third one is a bit more difficult to handle, and it defines a pattern. A pattern here is seen as the class of all distributions that in some sense bear some similarity with a given distribution here. As seen through some functional, here the functional are spacing induced by some sampling. The geometry of such classes is difficult as such, and inference through variational methods in those classes are not obvious at all. We may also consider here very important classes of models which are associated to classification, and the basic ones is the logistic model. You can see that we have two groups actually, which this is supervised learning. So we have two groups. There is a covariate for each individual and its label. And we have a representation of this model through what is written here. That means the probability of being in a class given the covariates. This, by simple Bayesian formula, leads indeed to a model which is at the center of the slide, and the comment is just after. We see that the model here indeed is the couple of distributions of the covariate given the group. And what is important for the next slide actually is the fact that this model is defined through a ratio F0 divided by F1. So those are models for which somehow we have some knowledge on the likelihood ratio. And this will be an important fact for the inference through variational methods. We now come to a variational representation between the Q of the divergence between Q and P. This is a formula that somehow seems familiar. Indeed, the mapping from Q to the divergence is convex, so we are not such surprised to have such a representation. And this representation has a peculiar feature for people who are, let's say, who know about theorems like Sanoff-type theorems in probability. The representation of the Kullback-Leibler divergence is the same somehow, where the sup is taken on classes of function, typically measurable or bounded functions. Now we take a small example. We take P and Q being two Gaussian distributions on R with same variance. Then clearly what happens is that the sup in this formula is achieved on polynomial of degree 2. So we see that the usual representation of divergences as induced as rate functions for large deviation probabilities for empirical measure is obviously valid, but does not lead achievement in the supremum. So the interest of this formula for statisticians is the fact that there is achievement in the formula here. And since globally we are interested in taking the infimum upon Q of the divergence, obviously we will have to know something on a class of functions that would contain actually the likelihood ratio at the projecting point itself. So this is the reason why this formula somehow is not at all in the same range of formula as globally considered when we look at those kinds of objects. Here is for parametric models. We see that we are able in this case to individualize the class F, which contains actually the likelihood ratio, and this is indeed the class of the phi prime p theta divided by p alpha is indeed the smallest class, which without knowing p theta contains indeed phi prime of p theta divided by p alpha. So this is indeed the class where statisticians would look for the optimization. The second case is just the same approach for logistic models, since we saw that logistic models were also defined by likelihood ratio. So the class of likelihood ratio is indeed necessary in order to solve the problem. So this is a main problem we have through variational methods, is that they require some basic knowledge on the locus of the projection of Q of P on the set omega, in order that we're able to give some idea of what we're looking at. And indeed, we're looking at the likelihood ratio. Now, on a statistical standpoint, obviously, we see that, for example, in the first line here, theta t, p theta t, which is the real source of the data, is obviously unknown. The interest of the variational form here is to split the representation of the divergence in two integrals. The first one is not pertaining to the source of the data, and the second one is. So we can simply substitute the integration with respect to the measure of the data by its empirical counterpart. This leads to this formula up there. The interest of the variational representation is also the following. You see that d hat in the display here indeed is not just an approximation, say, it is not a divergence in itself. I will just explain this shortly. If p theta is absolutely continuous, then obviously the empirical measure, which is discrete, would lead that the divergence would be infinite. So this formula with the hat indeed is not a divergence, but it converges actually to the divergence we want to estimate. This is important because you see that we have here finite values for estimates of the divergence, and this does not need any smoothing or grouping as is done usually, and this solves the problem of absolute continuity between the empirical measure and the model through this representation. That's the same for the case for the logistic, obviously, and this leads to various methods of inference. I will not develop this, but this is the principle, let's say, of what we call variational inference. Now, here, what we have is the fact that we have seen that, okay, so this is, okay, this is just what I said, that somehow the problem is to individualize the class F, and now the point is the following. If we cannot have some idea of the class F which would contain indeed the projection, so what would we do? And this is the focus here of the, so this is why we have developed with Wolfgang some methodology in order to handle more involved situation where the geometry of the class omega is somehow more complex, and this will be achieved through a change of paradigm, and for which we will consider the various divergences which we have as resulting from result of probabilistic nature and representation. So I will give the talk to Wolfgang for that. Thank you.
So, as Michel just said, we are now changing the paradigm or the method to approach optimization problems. So recall again, we have a model class omega, or you would call it constraint set, and we would like to compute the minimum of a function phi over the constraint set or model class omega. So that's how we approach it. We would like to find a function g and a sequence of probability spaces, and on them a sequence of random variables, just that the desired minimum of phi over the model set omega is of this nature. It's g of minus the lim of 1 over n of log of the probability that the Cn hits the model set omega. And we call that a pure or pair simulation approach to the minimization of functions. Okay? So today, as Michel already said, we concentrate on the phi divergences in the first component Q, but we have a second component P, which plays the role, say, maybe kind of parameter, but keep in mind this parameter is a probability measure, okay? Good, so that's our paradigm. Okay, let's move over. So, and then of course, you take the usual approach. You cut off the sequence at approximation step capital N, and then as a last step, you estimate the probability of hitting omega via maybe a naive estimator, but it can be a more sophisticated simulative estimator, for instance, through importance sampling. Okay? So you should always keep in mind we replace an optimization problem by a simulative counting problem. Yeah? Our method is dimension-free, and almost no assumption like convexity on the model set or constraint set is used, so it can be quite nasty. It can be also highly disconnected, whatever you like. Okay, and our method is precise because it converges in the limit. So, for instance, just to give you an idea about the estimator here. So, for instance, you construct, you simulate L independent copies of the Cn's, and then you just take the average of the number of hits of the Cn's to the constraint set lambda. So it's counting. So we first start, so I will give you several steps, you see. We first start with maybe the uncertain case, yeah? Or a probabilistic case. That means the P, the parameter, which is a probability measure, is unknown, yes? Okay. So today we work on the space of discrete measures on capital K states, and K can be very, very high, yeah, no problem. And depending on the situation, we take probability measures or non-negative measures or signed measures, yeah. And as usual, we identify them with vectors, okay, K-dimensional vectors, okay. That's what we do. Oh, sorry. So we need a basic assumption on the parameter capital P, which is a measure. Yeah? So we suppose that we have data xi coming from the measure P in such a way that the empirical distribution of the xi's converge against the P. But not necessarily it means that the xi are IID. They can be also ergodic Markov chains or autoregressive chains, whatever you like. whenever this condition holds, you are in the game. Okay? So, and of course, in vector form, this basically means that the histograms converge. Yeah? The histograms converge. So you see, what we aim for is to find basically a sequence of random variables Cn, which are now probability measures or probability vectors, okay? And in order that this works, the generator phi of the phi divergence has to satisfy certain conditions. Analytic conditions. You see, here there are some, you will see some more later on, but one assumption we require is very central. It's a cornerstone assumption. Yeah? And that's the following: the divergence generator phi should be the Legendre or Fenchel-Legendre transform of the log moment generating function of a probability measure zeta in such a way that zeta has light tails, in this sense that it covers this, and it's on the neighborhood of 0, the moment generating function should be finite on the neighborhood of 0, okay? That's our basic requirement. Then our method will work, okay? Okay. Because what we do is, from the zeta distribution, we sample a family of random variables W, yeah? And then we construct a normalized weighted empirical measure, yeah, of that form. So the first ingredients is a partition of 1 to n, and the partition comes from the random variables xi, which are related to the parameter capital P, okay? So these partitions are random, they change with the sample, okay? Okay, and then we collect, we sum up the W's on each of the partition, yeah, and then we normalize, yeah? That's it, okay? So this is a k-dimensional vector, you know, and the sum of random components is per construction 1, yeah? But the components can become negative, yeah? Because you will see later on maybe the W's may be Gaussian, yeah? So they may become negative. So after all, this normalized weighted empirical measure is a vectorized random signed measure. Okay? And this will be basic ingredients for us. Namely, we have to take an intermediate step, because you see we take the constraint set or the model class omega to be in a probability simplex. And since this is flat, we have to do first an intermediate step. Yeah? Actually, we consider these divergences. So we take the inf over m of the phi divergence between m times q and p. Huh? One can prove also that this is a divergence. Yeah? And for this, we get the following result, basic result. You see, here is our divergence, and the inf over the model class of this divergence with respect to the first component can be just achieved, as I said before. So the g function here actually is the identity. Yes? So we have minus limits of 1 over n log times probabilities that these normalized weighted empirical distribution hits the model class omega. Yeah? And the expectations here are the conditional expectations, conditioned on the data of the xi's from 1 to n. Huh? And this works, you see, for all sets of probability vectors, models of probability vectors, which satisfies just these two natural conditions, namely the interior should be non-zero and the closure of omega should be the closure of the interior of omega. Very simple. So omega can be very nasty, but of course, this is not satisfied by parametric models. So these are kicked out. But however, for parametric models, there exists a vast amount of other methods. You know, it's basically classical optimization. So we deal really with the hard case with the non-parametrics, okay? So this works. That's it. But so far we have an intermediate divergence. But this M minimization can be solved, for instance, for the very important class of power divergences Michel already mentioned. Yeah? So here, again, you see the generator. Well, you have to do some corrections for the other ones. I don't talk about it. So this, what you have seen before at Michel's talk. This is the generator. And here are the divergences. Basically, it's a formula like this, but see, for later purposes, we also talk about non-probabilistic cases. So I included now the most general cases. Yes? So in the probabilistic case, the sum of the B case is 1 and the sum of the Q case is 1. So things simplify quite a lot. Okay? So why are these so important, the power divergences? For 3 reasons, at least 3 reasons. Namely, firstly, there are widely used special cases. Michel already mentioned most of them. Yes? The second point is that these power divergences trigger widely used other divergences and similarity measures. And the third point is that they trigger also several widely used entropies. Okay, and keep in mind, since we can simulate, we can solve optimization problems on power divergence by Baire simulation. We can also solve optimization problems of all these divergences and generalized entropies, you will see on the next slides, with our Baire simulation method. And you know, I've prepared 5 or 6 slides. I will not go through them, but you should just see how rich the offspring and the class itself is and the offspring of it. So let's start. So first of all, there are several different names coming from several different research fields already for the power divergences. That shows their interest in a lot of research fields. The special cases, Michel mentioned already, the Kullback-Leibler, or it's also called relative entropy in physics. You know, we have the reverse one. We have the Pearson chi-square, etc. We have the Hellinger distance, etc., etc. Okay. So here, it's just a couple of citations of papers where power divergences are used recently. You see, we start here from 2019, so the last 2 years here, and all sorts of research fields like machine learning, pandemics modeling, medical imaging, semiconductor chips, etc., etc. Yeah? So it's a very vast and rich applicability of the power divergences. Now about the connected similarity measures or divergences, a very important notion is also the Hellinger integral, which is basically a linear transformation of the power divergences. Yeah? And also important, the Renyi divergences, which is basically the log of the Hellinger integrals. And you can see there's a huge amount of recent application. So it's really cutting edge research in other research fields where these offsprings and the power divergences are used, okay? Like coding, cryptography, robotics, autonomous driving, genetics, meteorology, material science, etc., etc. There are some special cases, namely the Batteria coefficient is also very well known in engineering, and the Batteria distance, okay? So how about the entropies? So far, we have talked about that the P is unknown, but later on I will talk about the case where the P is known. Let's talk at the moment that P is known, namely nothing else but the uniform distribution. Yes? P is the uniform distribution, and if you plug that in, for instance, the Hellinger integrals, then you end up with a sort of different important indices in many research fields. But you also end up with the Euclidean gamma norm. Okay? If you have to optimize your norm on a nasty set omega, okay, we can help you. Okay, and of course we have the Renyi entropies, which are very important. The Zallis entropy is very important in physics, you see. And, oh yeah, the Renyi entropy. So, you see. And of course you also get the Shannon, the classical Shannon entropy, yes. And, okay, so all of these can be minimized or optimized by means of our pair simulation method. So now we have talked about, say, we have talked about incentives and children of power divergences. Now let's return to the techniques, okay? I promised you that you can solve the M minimization by means of classical methods, and here is the solution. We've got here it can be then represented as G of the desired power divergence, okay, and then by rewriting this, we end up with the inf over the power divergence to be represented by this G of the simulation part we are aimed for, okay? So, good. If the M minimization cannot be solved explicitly, at least we can give some bounds which are marked here at red. I will not discuss it here, but I would just tell you, for instance, as an example, important example, the Jensen-Shannon divergence corresponds to the generator phi of this form, and we end up like bounds like this, okay? That means we can go along also in such a case. So recall that we would like to have the W's which have the distribution zeta, and zeta should satisfy this representability, okay? So the questions arise, given the divergence generator, how can one prove that such a zeta exists? And how can one construct it? It's a very important question. So in order that we have a chance that this works, the generator phi has to satisfy certain analytic properties. I will not list them. You can see different situations here for the power divergences, how the generator would look like. I will not comment it, but there is one very important analytic property the generator must satisfy. It concerns about the Fenchel-Legendre transform of the generator. And this should be in such a way that an exponential of a linear transformation of the Legendre must be either absolute monotone or exponentially convex, depending whether the edges of the effective domain of the generator phi are finite or not. Yeah? Okay. So summing up, what we've done is we started with the divergence generator phi, we constructed the Legendre, and take some exponentially linear transform of that, and then we gave some sufficient conditions that this is really a moment-generating function of a unique probability measure with light tails, namely this absolute monotonicity or exponential convexity. Okay? However, if we want to find the concrete zeta, then typically you should know the Legendre, and this can be sometimes hard. You could also go the other way around and start with a probability distribution zeta with light tails, compute its log moment generating function, and take the Legendre of this, and this then is the divergence generator phi. But also this way can sometimes be hard to make explicit. So in order to ease the things, we give now a kind of intermediate construction method, for which we just use functions phi with very simple properties, namely f with very simple properties. F should be infinitely differentiable, and it should be strictly increasing. That's it, basically. Huh? So, and then we end up with this theorem. So see, from the f function, capital F function, we compute both the divergence generator and the candidate for the log moment generating function. Then you still have to look for the absolute monotonicity or exponential convexity. Yeah? And so there are quite involved formulas, because we also introduced an anchor point C where we could shift things. We can shift the domain and stuff like this. So you can, with this, we call it the F theorem, we can generate many new classes of divergences. Yeah? For today, I only show you how this works with the known power divergences. The F function is basically just a power function. Yeah? And then we end up with the generator you have already seen at Michel's talk. And here is the corresponding log moment generating function. Okay. And the interesting thing is, the power divergences have a parameter gamma and also a scaling C tilde, okay? And the interesting thing is that as gamma varies and also the C tilde varies, you end up with quite a drastically changing class of corresponding zeta distributions from which we simulate the W's. For instance, if gamma is smaller than 0, then we end up with a tilted stable distribution on the positive real line. Okay? If gamma is between 0 and 1, we end up with a compound Poisson gamma distribution. If gamma is larger than 2, we end up with a distorted stable distribution on the whole real line. Yeah? If gamma is 2, we end up with the normal distribution. If gamma is 1, that means we have the case of Kullback-Leibler information divergence or relative entropy. We end up with a Poisson distribution. And for the reverse Kullback-Leibler, we end up with a gamma distribution. So we have discrete distributions here, continuous ones and mixtures of such kind of things. So it varies quite drastically. So it's very interesting. But of course, you can, as I said, we can give a lot of other examples. Maybe just to mention another one is the Jensen-Shannon we have seen before. Here's the generator again. And this corresponds to a negative binomial distribution. Okay? So, and here are some more classes related to linear combinations of gamma distributions. You see the divergence generators are already quite involved. Yeah? Okay. So now, so far, now I talk about deterministic optimization problems. Yeah? That means, so in 2 steps. Yeah? First, we have the context 1. We replace the unknown vector P in the probability simplex by a known vector P in the probability simplex. Okay? P is now known. Yeah? And we also flexibilize that the constraint set can be now in the form A times a probability vector set, yeah? Where A is a positive constant. So that means the constraints are of the form that the sum of the components of the vectors is A, but not necessarily 1. So that gives us more flexibility. And then we can go along as before, with the only difference that now the partitions are now deterministic. That's the main difference. The rest is more or less the same. Yeah? So again, we can solve this double minimization for the power divergences to have the desired minimization. And then you can simulate all the Rayleigh divergences, etc., etc. And of course, we can also have matrix versions of that, tensor versions of that. And also, just simple separable quadratic minimization problems, which are purely deterministic of this form, can be solved by just simulating the W's via Gaussian random variables. So it's quite a comfortable method. And yeah, with some retransformation tricks, we even can solve linear, the optimization of linear objection functions with constraint sets on gamma norm spheres. But these constraint sets can be very nasty, non-convex. They can be highly disconnected, whatever you like. Yeah? And for instance, we can develop, or we have developed, a new approach, a new relaxation approach to discrete combinatorial optimization problems. For instance, the most famous one, namely the traveling salesman problem, we can attack with our pair simulation method. Okay? Good. Now, context 2, we take one step further. We replace the known vector P from the probability simplex by an arbitrary vector P having purely positive components. That's it. Huh? And this pointer here. Yeah. And we take some rescaling. Yeah. And then again, we have this crucial representability. And here's the theorem. And you see, we can tackle the desired optimization of the phi divergence immediately without having this double minimization. And then we get that the inf can be represented as minus lim of 1 over n log of the probability that this guy hits a transformation, a rescalation of the constraint set, again with the same sort of constraint sets, omegas, which just satisfy these two simple conditions as before, but now, of course, in the full topology, and not in the topology of the simplex. And this means that the probability, so when omega is a probability set, is now kicked out, yeah? Because it does not satisfy these conditions, of course. So, but in a sense, this is even simpler, you see? Because we have a constraint less. We don't have the sum to be 1, so this is a one constraint more. Okay, so we are nearly finished. So just my summary, you see. We solved optimization problems, you know, certain ones and uncertain ones, by a dimension-free random pair simulation method. Yeah. We used the widely employed phi divergences, and we were on a discrete setup, but maybe with a high number of states. Yeah? So it can be a high-dimensional problem. Yeah? And we needed almost no assumption like convexity on the constraint sets. So, and our method was precise because we had the convergence theorems. Okay. So, and basically what we did is, you know, we estimate then the probability, you know, we count the hits of the CNs to the constraint sets. So it's a counting method, so to speak. And by this counting method, we solve deterministic or probabilistic optimization problems. So as a final sentence, I would like to say, please always remember, when you have a distance or an entropy optimization problem, you can count on us. And here I would like to finish my talk. Thank you very much.
Okay, thank you very much. Very interesting talk and very dense. Hello, Wolfgang. Yeah, maybe we should ask whether there are some questions in the audience or remote people.
Omega constraint is open. How you calculate the size of omega with number n? Because to have to put your n, you need to have estimation of the number n.
Yeah, this is actually a question.
Michel, on répond.
indeed, this is a question that should be addressed. The relation between the complexity, first, let's say the dimension of the set, so number k, and the number of, say, the sample size, which allows to do that. This, well, this is accessible. I mean, it has to be done, but it's something that has to do with the limit approximation result in the large deviation theorem globally. But this is something, there are bounds. We can do that because if we look at theorems of type of sum of time theorem, and those are sum of type theorems pertaining to weighted empirical measures. So we have bounds. There are, for finite n, there exist bounds for upper bound and lower bounds with respect to the rate, to the large deviation rate, and this is precisely the tool here. Those bounds are known as Caesar or others bounds. So that this is accessible. We did not write it down, but there are tools to handle the relation between the complexity of the set and indeed the sample size for which an accuracy can be achieved. Merci.
So,
I have a question if I can ask. I don't know if you can see me. Sorry for the very naive question, but I may have missed something essential about your talk. What does a more general phi divergence allow you to answer than the ordinary relative entropy could, let's say in some physical problem? So what do you gain by using more general phi divergence?
So did I understand correctly that you said, well, what is the use of not using Kullback-Leibler divergence?
For example.
Yes. The answer is very simple. You see, for instance, if you minimize, if you get the minimum distance estimator, if you use the Kullback-Leibler divergence, then you end up exactly with the maximum likelihood, okay? But we know, all we know, that the maximum likelihood is not very robust against outliers. And there's a vast machinery that, for instance, if you take different sorts of divergence generator, then you can have different, you can have more robust estimators. And for instance, this was started by Lindsay in 1994 in the Annals of Statistics. He developed a tool which is called residual adjustment function, and actually it's related to one of the quantities I showed you. And you can further on, we had a whole very long paper, 40 pages, with Annalena Kieslinger 4 years ago, where we even extended it to Bregman divergences to have similar robustness indicators. So that's maybe
I will also give an answer to that. This is an important question, actually. For parametric models, indeed, the choice of the divergence somehow can be handled with respect to robustness properties or others. Now, the fact of choosing one divergence with respect to another is widely open, but in a number of situations. For example, the chi-square divergence, obviously, is the integrated or expected value of a relative or squared relative error. So we know what we measure when we use a chi-square. We know what we measure when we use L1, variational distance, and others. Otherwise, the relation between the divergence and the setting is open. It could be related to a Bayesian non-parametric approach, for which, indeed, the choice, the minimum divergence estimator would indeed coincide with minimum, a posteriori, say, Bayesian estimators, but this is still an open problem.
maybe you take your mask off. P is where the xi's come from. and the xi will trigger the partition of 1 to n. So you partition concerning, so you have k data points, okay, you count how often the xi hits the first data point, yeah, and then you have a certain partition, one part of the partition, and on those you sum up the w's and maybe renormalize them, and then you have the first component of our weighted empirical distribution. And you do the same, so you have the second data point, you count how often the xi's hit the second data point, then you have a certain partition or part of the partition, okay, and then you sum up again some omegas on this, and then you rescale, and actually one can have, since most of the distribution, you see, the distributions, if you know it for one W, then you also can immediately count it, give the explicit solution or the explicit distribution if you have a sum over independent omega i's. For instance, if you have normal distribution, then you don't have to, then you can simulate blockwise, so to say. You have even a more shortcut than here. Yeah, that's why I showed this tilted distribution. So we identified, I don't know, 10 examples, and there are 30 more examples in our drawers, okay? For the next publication, yes. And in the paper you can read it, so I think the paper is 94 pages, so it's nearly 100 pages. So we have a lot of, I think we have 20 examples in there, so if you're interested, please read the paper, yes.
I have a last question. In slide 19,
Okay.
no,
Yeah, that's good.
no, you put what you call
Where do I have to press? Here? Here?
is it possible?
Okay.
19.
Voilà.
Yes, the cornerstone assumption, is it a limitation to exponential families or not?
No, it has nothing to do with exponential family. I mean, it's nothing to do with exponential families.
So,
No.
okay.
It is a different construction. What is known for exponential families is a classification of distributions according for natural exponential family by their, say, variance function, which are of power type. It has some similarity with what is done here, but here the purpose is quite different as such, and the representation is quite different. Indeed, the F theorem, which is mentioned here, allows indeed to extend the construction of the simple power distribution, which is adapted indeed, which could be seen partially, because there are in here a number of situations where we need some after transformation, actually, extra transformation. So, but the F theorems allows to recover indeed the classification of the natural exponential paradigm.
And maybe if I may add, so with our F theorem, we can, if we rescale and retransform something like that, I think we can easily construct dozens of new exponential families. With it's vaguely connected. So, but you can have analogous methods to also construct exponential families. Yes. Are there any more questions? So,
You want to conclude, Frank?
Oh, I just want to thank Michel and Wolfgang for this very interesting talk. I think it's quite inspiring, and there's a lot of questions like geometric interpretation, and also the link between divergence and entropy in the continuous case is also very interesting. But we are behind schedule, and I think it's better to proceed with the program. So thank you again, Michel and Wolfgang.